Welcome back. In this lecture, we're going to talk about the phenomenon of overparameterization and interpolation, which is basically a quite essential component in the success of modern deep learning models. In particular, as we're going to talk about in the lecture today, we're going to see that thanks to overparameterization, our training problems are going to have some favorable structures, meaning that not only we can basically increase the capacity of model and potentially learn richer structures, but we can solve the optimization problem faster. We can solve the optimization problem potentially globally and find an optimal solution despite the inherent non-convexity of the training task. And also we're going to talk about consequences for generalization. So that means that thanks to overparameterization, we could potentially also improve the generalization capability and the test performance of our deep learning models. So let's talk about the setup, and first of all, let's see what I mean by overparameterization. Okay, so deep learning models are overparameterized, and that simply means that if W denotes the set of our parameters, the set of the weights of the neural network, and if its dimension is D, then D is larger than the number of data points that we have in our training data. So in particular, if N is the number of data points, the condition that D is larger than N means that we are in the overparameterization regime. Okay, and so what does that mean? Okay, so quite simply, that means that there are more unknowns than knowns, right? So we have a very large degree of freedom, W, and we can leverage that to fit basically N data points. And theoretically, we can basically fit the data points perfectly. And not only that, but also there are multiple ways to fit the data perfectly. Okay, so in scenarios where we have an underdetermined system, such as this, we might have multiple global minima. Okay, and this is also something we talked about before in the context of second-order guarantees, and we saw that generally in non-convex problems, we might also have multiple global minima. Okay, in this case, having multiple global minima arises from the fact that we are in the overparameterization. Okay, so effectively, as I just mentioned, that means that there exists at least one parameter W star that can interpolate all samples. Okay, so what does that mean? Interpolation. What does that mean? It means that W star, which is the minimizer of our empirical loss, okay, is also a minimizer of the individual loss samples. Okay, so this is the best W that you can have for every single data point. Not just on average it's the best, but for every single one of them, it's the best. So it fits every sample. It interpolates every sample in our training data. Okay. Now, equivalently, especially if we assume that there is no constraint or anything like that, when we talk about optimality, a necessary condition, of course, is first-order stationarity. So that basically means that the gradient of the average loss at W star is 0, because W star is an optimal solution. But also, thanks to interpolation, the gradient of W star at the gradient of individual loss samples with respect to W evaluated at W star is also 0. Okay. Now, for the purpose of this lecture, then we're going to refer to this as the interpolation condition. Again, interpolation is a byproduct of overparameterization. Given that we have more parameters than the number of data points, we can fit the samples in the training data perfectly, and as a result, our global solution W star is also the minimizer of the individual loss samples. And in particular, this condition, the interpolation condition, holds. Okay. Now, why are we talking about this? Because the reason for that is that we're going to show that thanks to this interpolation condition, or in particular, if this interpolation condition is satisfied, then it's possible to have faster convergence guarantees for stochastic training algorithms such as SGD and its variance. Okay, so we're going to start by first establishing faster guarantees, and then as we make progress in this lecture, we're going to talk about finding higher quality solutions, notably global solutions, as well as consequences for generalization. All right, so again, we're going to talk about interpolation and show the benefit of overparameterization for the simple case where we are training our deep learning model using our simple and nice algorithm SGD. Okay, so let's first recall the rate of convergence we established for SGD for broad non-convex functions that were smooth, meaning that they had a Lipschitz gradient. If you recall, this is a result we established earlier in the course. And we said that basically we can find a first order stationary point with this specific rate. Okay, so the norm of the gradient squared is bounded by two terms, 1 over t. This is basically the rate of the gradient descent, plus a stochastic term. So it depends on how good our stochastic estimation of the gradient, true gradient is, right? So we assume that we have access to a stochastic first order oracle with variance sigma square, and this basically finds its way in our convergence guarantees. So we talk about ways to reduce the variance, for instance, through variance reduction techniques and control variates, as well as connection to momentum. Here we're going to see that, in fact, we don't need to do those. We don't need to take those actions. Thanks to interpolation, which is itself a result of overparameterization, variance reduction happens for free. Okay, so that's what we want to establish. Okay, in particular, we're going to argue, as I mentioned here, through this proposition, that the variance here, sigma square, is not constant. So, in some sense, the stochastic first order oracle that we talked about is a little bit pessimistic, especially when it comes to training deep learning models, overparameterized deep learning models. So the variance is not constant, rather it decreases as the algorithm makes progress. Okay, so there is therefore a virtuous cycle, right? So the algorithm makes progress, the variance reduces, which means that the algorithm is going to progress even faster. And we keep doing so until we converge to a first order solution. Okay, more formally, let's consider a simple setting where we can demonstrate the benefit of overparameterization. And in particular, let's consider the scenario where we are minimizing the average loss. Okay, and we assume that each of the individual loss samples, this small l, is L smooth. Okay. Furthermore, we assume that the interpolation condition holds, meaning that the gradient of f at W star is equal to the gradient of L at W star for each sample equal to, let's say, 0. Now, what we're going to show is that if you just use the simplest oracle, meaning that at every iteration you sample one of the data points uniformly at random, then the variance, or in this case, the second moment, which itself bounds the variance, is bounded by 2 times the smoothness constant L times the suboptimality gap. So what does that mean? It means that as you are approaching a solution, variance reduces. Now, one thing we're not going to discuss in the class because it is a trivial extension of the analysis we talked about previously for SGD, is that you can leverage this proposition and show that the rate of convergence for stochastic gradient descent will improve to 1 over t. So in particular, the second term, which was as a result of the stochasticity of the oracle, completely vanishes. So that basically means that we are getting variance reduction for free. We don't need to do any of the techniques we talked about theoretically, like the momentum approach as well as the control variates. And this is the best we can hope to happen. Okay, all thanks to overparameterization and interpolation. All right. So this is therefore the first nice property of having overparameterized deep learning models: faster convergence. And given that the proposition and its proof is quite simple, I'm going to actually go over the proof of this proposition in the lecture. Okay, so it's just a couple of lines. We want to bound the second moment. So let's calculate what the second moment is under our specific stochastic first order oracle, which basically samples one of the data points uniformly at random. In particular, this is my second moment. And this is an expectation that I can quite simply calculate, right? So it's just the average of the norm of the gradient square for the gradient of the individual loss samples. Okay. All right. Now here is what we're gonna talk about. Okay. So, and we're gonna leverage. There is a consequence of L smoothness that we haven't talked about in class before, but we're going to actually prove in the next slide. And that says that if you have a smooth function, the norm of the gradient square is bounded by the suboptimality cap. Okay? So here we assume that each of the individual samples is L smooth. Therefore, that means that this gradient is bounded by 2L times the value of the loss minus the minimum value of the loss. And here Wi star is basically the minimizer of the loss of the individual, loss of the sample I. Okay? Now, in general, Wi star is not equal to W star. Or, but for overparameterized case, we can basically make an assumption that this is correct. Right, so as we talk about, as a consequence of overparameterization, we have the interpolation condition, which basically means that the loss at Wi star of Zi is basically equal to, or rather, if W, thanks to in overparameterization, W star and Wi star are the same when we have interpolation. But in general, that's not the case. Okay, so now we're going to plug in this equation 6 in equation 5. Okay, so that means that the second moment is now bounded by 2L, the average of the individual suboptimality gaps. Okay, now as I just mentioned, thanks to interpolation, Wi star is equal to W star. So what we can do is to just simply leverage the definition of our function f, meaning that function f is nothing but the average of the individual loss samples. If you plug this into equation 7, then the proof is complete. Again, we just established that thanks to interpolation, the second moment of our stochastic oracle, which is trivially a bound on the variance, is itself bounded by the suboptimality gap. As the algorithm makes progress, the variance reduces, and we can leverage this to get faster rates for the convergence of SGD and its variance. Okay, so that's the proof of the proposition, but we sort of leveraged a consequence of a smoothness in the proof, and I'm just going to spend a couple of minutes going over the proof of that consequence. Okay, because again, that's also quite simple, and it's a nice property that typically we can leverage when we want to analyze training algorithms, particularly if you're looking for relaxing the existing assumptions, or when we want to establish convergence under overparameterization regime. Okay, so what's the idea? The idea is that we just start with our usual definition of a smoothness. Okay, we said that there are multiple equivalent definitions for a smoothness, right? So gradient being Lipschitzness, gradient being Lipschitz. The function has convex upper bound and concave lower bound, and also if the function is twice differentiable, all the eigenvalues of the Hessian are bounded. Okay. Now we start with this definition, and this we know that this holds for any pairs of x and y. In particular, the condition holds for this specific y star, which is a function of x, which effectively minimizes the right-hand side of equation 8. Okay, excuse me. Now, this is a strongly convex problem because it's just a convex quadratic function of y. So that means that there is only one such y star of x, and I can find that quite easily by taking the gradient and set it equal to 0. If you do that, you're going to find that the y star of x is going to be x minus 1 over L, the gradient of our function at x. Now, we just plug this into equation 8 again, into our definition of smoothness, and note that whatever this y star of x is, its function value is at least as large as the optimal function value f star. So therefore, we use this fact, do some very simple algebraic manipulations, and we arrive at this condition, which we crucially leverage in the previous proposition to establish the benefit of interpolation in terms of providing us free variance reduction and thereby leading to faster rates of convergence for the stochastic gradient descent algorithm. Okay, so this was therefore the first nice consequence of overparameterization, faster convergence. In the next part of this lecture, we're going to talk about another consequence of overparameterization, which basically is saying that under certain conditions, particularly if the initialization is nice, not only we can converge faster, but also we can converge to an optimal solution. Remember, all we showed here was that the convergence to a first order stationary point is faster under interpolation. But it turns out that we can strengthen this result under certain assumptions. We're going to talk about those in the next part of this lecture. I'll see you there.